Continue. First, I would like to take this half an hour of time to review something we have did for the last 2 years, and then for the last maybe 15 minutes, I'll tell you some application of this to the idea of M5 ring. So, this doesn't work. So this talk is based on material which I have done in the last 2 years, postdoc here, using now and Wu. So this is the outline of the talk. I'll talk about the phenomena in quantum field theory. So this is something which one can calculate in boundary conformal field theory using standard techniques of quantum field theory. Take two Simon diagram computation in general, but we did it in a more elegant way by determining this exact form of induced error which I will explain in the talk by establishing a relationship with anomaly. And I will calculate the same thing again using ADS BCFT. So it's an extension of the standard ADS CFT to the case of CFT with boundary. And then I apply this to 6 dimension. 6 dimension is an interesting case for studying the extension of quantum field theory idea in string theory in particular. So just I have 2 motivations. The first is M5 ring. M5 ring is not so fashionable here at this time, but like 10 years ago or 20 years ago is a fashionable subject. So in string theory, in 6 dimension, there's a decoupling limit of M5 ring, which gives rise to a 2.0 maximal supersymmetric conformal field theory in 6 dimension. It's like 4-dimensional Yang theory. This theory is supposed to have some gauge symmetry based on the number of breaks put together. So the fundamental description is complicated. People have tried also to come up with some low energy description, which I will not go through. So although there has been different attempts to understand this theory, but so far there's no convincing check of any of these proposals that these are correct. Because to make a correct check, you need to have a convincing, look like my alarm which wakes up in the morning. So you need a convincing calculation which establish something correctly, and then check it against other calculations. This has been done. Anyway, but no matter what the fundamental theory is we do expect some criteria this theory has to satisfy. For example, it has to contain a non-trivial interaction of the 2.0 super multiprep. It should contain BPS state of self-built strings, and it should explain the S duality in 4 dimensions. And it should also explain this entropy behavior. So in the context of ADS CFT, the 6-dimensional 2.0 field is due to some 11-dimensional theory with ADS as background, M field on top ADS 7 background. In this background, you can introduce black hole, when the entropy can be computed for those black holes and have the entropy dependence. So this should be explained in terms of the field theory also, some counting of state. I just would like to add a new item for this list to be explained. So this item is that as usual, any theory, even though it's conformal, can carry conformal anomaly. If you put a background, for example, the background itself will create conformal symmetry and defines the anomaly. And this anomaly usually are constrained by descent equation and the structure of this gauge structure of the theory. So it's usually computable and well classified. So for example, in 6 dimension, we know if we turn on a fuzz background, free-form fuzz background, the Weyl anomaly has to take this form. This is just a definition of the Weyl anomaly. For effective action, you scale the metric, the third derivative of the scaling of the effective action give rise to the anomaly, the Weyl anomaly, and it has to have this form. This is in the presence of a form field form plus spectrum. The same story you can do for metric. So this is something which we derived in this study. So any fundamental definition of the theory should reproduce this equation here. B is a coefficient which it's like overall coefficient which determines this anomaly. This contains the physical data contributing to the anomaly. For example, the number of multiplier or beta function, that kind of thing. So this is the first motivation. The second motivation is that we would like to study lawful effect of boundary Common field theory. In principle, we have the Common field theory. It's interesting already, but if you introduce the boundary will break some of the conformal symmetry. So it allows you to have an even richer physical phenomena in the theory. So it's even more interesting. Of course, it's even harder. So what I want to show you is that here it's possible to get hold of some new phenomena and understand them exactly by going to the roots of anomaly again. So for example, I will show you that the Casimir effect, which is just a standard Casimir effect between capacitor in vacuum. You get Casimir forces. Those kind of Casimir effect can be understood from anomaly. That's one thing. Also, I will generalize that phenomena. The Casimir effect is a phenomena between a boundary of the boundary in the presence of a vacuum in the presence of boundary. It's an energetic response of the vacuum to the presence of a boundary. There's a generalization of this effect. You can say, oh, some type of boundary, instead of considering any energetic responses of the vacuum, what about if I introduce again some background flux, for example, EM background? How would the vacuum respond to the presence of EM background? So I will show you that there's a new induced current. For example, in this setup here, I have a simple flat boundary with a B field going in this direction, and turns out there will be a current just going in this direction with a dependence on the distance from the boundary in this way. So this is can be established exactly, both by doing a BCFT analysis or by going into homography. So this is what I'm going to show you. So the induced current can be understood both in terms of Weyl anomaly and ADS BCFT, and of course the two are also related. That's why I draw this triangle here. So in the last part of my talk, section 3, I will apply this idea. So this is established in general for any dimension. I will apply this to M5 ring. In the case of M5 ring, is the structure of Weyl anomaly from the fundamental theory is not known. So this you can put a question mark here. On the other hand, we know how to derive the induced current using ADS BCFT. So we can reverse the direction of the triangle. We can start from ADS BCFT, derive the current, and then derive the form of Weyl anomaly. This is what I claim in the beginning. We can have arrive at a new criteria for the structure of Weyl anomaly in 6 dimensions by going through this logic here. So, any question?
So as the boundary shifting technique itself is not related to M5 plane dynamics.
No.
So do you have some advantages of the boundary shifting approach?
Yeah. So as I said, this diagram is general. ADS BCFT, as you said, is general in dimension. So, but in 6 dimensions, we know basically we know nothing about the Weyl anomaly. So usually in quantum field theory, you compute Weyl anomaly by doing some loop diagram, usually one loop, for example. But in 6 dimensions, we don't have a fundamental definition of the theory, so it's not possible to do this computation. So this is unknown here. So in 6 dimensions, we can take advantage of this diagram and derive something about Weyl anomaly.
Okay, so you mean that Weyl anomaly is in 6 dimensions with the nice clue for some interesting dynamics of the fiber.
Yeah. So dynamics of the fiber ring is depending on if you have a fundamental definition of the theory first. So we can try to understand the dynamics of M5 ring using fundamental definition or using some effective description. So what I want to say here is that those approach, they may be useful, but it's not well established. So now we can have something concrete. This is something we want, no matter independent of the final answer. This is something we should aim to arrive. So this is something concrete to an answer given by other argument that any formulation should reproduce this. For example, then I can say to say Lima, tell me how your deconstruction can reproduce this answer for me. This is something exercise. So now let me go to the first part, first section. Let me just warm up. Well, it's not necessary warm up, but this is also new. But a Casimir effect in BCFT. Casimir effect, as I said, is related to energetic behavior of the vacuum in the presence of boundary. So in general, we would like to know not just the energy, but the stress tensor. So Casimir effect is about the stress. It's not just the force of the boundary. So in general, just a very general, generally, you can expand your stress tensor around the boundary. This is the proper distance from the boundary in this form. So the leading term will be x to the minus d, and then there's some coefficient here, and stuff like this. So this is coefficient. This coefficient here, first they carry dimension. So in d dimension, this will be the stress tensor will be mass dimension d. So for example, the leading term here, this would be dimensionless. So just by dimension argument, you can already settle down what this coefficient should be. They are given by geometry of the theory. For example, the leading one is basically the metric up to a coefficient which cannot be determined by symmetry or dimensional analysis. And then the second coefficient is this. Of course, there's also one important criteria you have to impose in order to get this expansion, which is the conservation of the stress tensor. So imposing the conservation of stress tensor, dimension, and then substituting this exponential expansion, one can solve for the coefficient. K is the extrinsic curvature of the boundary surface. The bar just means the traceless part. Okay, I don't go through the notation. It's not so important. But important thing is that there are some coefficient here. This coefficient are the physical part, physical data of the theory. The other one is the geometric about the geometry of the surface. So this coefficient, for example, in this here, you have alpha 0, alpha 1, and then you have some beta here for different geometric structure. This fixes the shape dependent of the leading Casimir effect. So you can call this Casimir coefficients, for example. Now, this is about the stress tensor, the asymptotic form of the stress tensor. There's another interesting quantity which is you can construct out of the stress tensor, or out of the trace of the stress tensor, is a Weyl anomaly. The Weyl anomaly, in general, consists of two parts. In the case of boundary, you have the bulk contribution, which is the integral of the integrand construct of the geometry, geometric quantity of the bulk metric, for example, and a boundary stress tensor, boundary Weyl anomaly, which is localized only on the boundary. So, for example, this Weyl anomaly will consist of an integral over the bulk and an integral localized on the boundary. Now, for the sake of this talk, I will be interested in only the boundary contribution. So when I talk about Weyl anomaly, I really mean the boundary Weyl anomaly. So in 3 dimensions, for example, we know that in 3 dimensions there's no bulk and Weyl anomaly. It's 0. There's only a boundary Weyl anomaly. So it's like this form. the boundary of the three-dimensional manifold is two-dimensional. So you get a integral which is just the order character of the boundary R, and then also you also get a trace k bar squared. And then in four dimension you get something like that. Just say like the boundary Weyl anomaly is also classified. It's well known. Yeah. So in this expression here, there are you have geometric data, also you have physical data. These are B. I use intentionally. I use B to denote the coefficient. So these are called the boundary central charge, like the cousin, the bulk central charge here. So coefficient in the bulk Weyl anomaly. There's something I call a theorem, just to draw attention. It's not really some fancy theorem, but it can be established quite generally, easily also. It's a relation between the variation of the Weyl anomaly, the boundary Weyl anomaly. So this is delta M is the boundary. With this integral here, this integral is computed in this way. You take the N-1 tensor with the arbitrary variation of the metric contracted, and then you regulate your manifold with a regulator. That's right, Fourier regulator. X equals 0 is the location of the boundary. So you calculate this integral. This is going to be divergent because of the asymptotic behavior of the stress tensor. I showed you. You have some divergence in the T. So you expect this to be divergent. Now you extract the logarithmic divergence term from this integral here. So the theorem is saying that these two will be the same. So this is quite useful because it relates the anomaly itself will involve the trace, the diagonal component. This involves all the components. So already you can see that this is quite useful because it gives you information from the anomaly and the diagonal component. You can learn about all the other components. Moreover, it's useful because the left-hand side is a total derivative. The right-hand side is not except this is exact is not exact. So this is some kind of interpolating condition. So using this, one can in fact determine the exact structure of T. So for time's sake, I will not show you the example. So so I have an example here for three dimension. It turns out one can use the boundary Weyl anomaly and determine exactly all those Casimir coefficients which appear in the stress tensor. So we let the Casimir coefficient, the English small letter is near the boundary central charge. So the statement is that the Casimir coefficient are not independent set of parameters in the theory. They are completely determined in terms of the central charge, boundary central charge of the theory. So now I go to the second topic. So that was about Casimir effect. So the story is that in the 70s already there are people who work on quantum field theory in curved space. After they finish quantum field in curved space time, they start to look for application. One thing they look at is quantum field theory in the presence of a curved boundary. The technique you have to use is similar, basically like Weyl function in a curved metric, something like that. So they look at this Casimir effect already. So Ken Dennis is one of the, I think he was a student at that time in the 70s. But what they did is basically case by case. So they did a free theory of free Dirac fermion or free scalar field. They compute this. So now we just show that actually in general you can determine the Casimir effect. But not just that, you don't have to compute this coefficient you compute actually is equal to the boundary central charge. Right? So we check, of course we check their computation. They satisfy the relation we derive. Not surprising. Okay, now the second application is about current, or I call transport here. So I will skip this motivation here. Just saying transport phenomena is something actually quite general. It's not something we invented here in the 80s already. For example, these people, due to different motivations from nuclear physics, cosmology, and condensed physics, they arrive at the same relation, which is a statement about the presence of a magnetic field, the standard B field, induce a current due to chiral anomaly. In this case, it's a chiral anomaly. So the chiral anomaly allow you to generate a current with the current B field. The current is in the same direction as the B field. You can have two current. One is a vector current, one is an axial vector current, and the coefficient depends on the chemical potential, which is you can have a mu left plus mu right and mu left. So you have vector combination of the chemical potential or the axial vector combination. So there's a similar effect which is called the chiral rotational effect, which is due to rotation. Basically, you rotate some plasma, for example. This will also give you a current in the same direction as the angular velocity. Again, it's due to chiral anomaly. Here, there's also a coefficient t squared over 6. This is again a chiral anomaly, but it's a gravitational chiral anomaly contribution. Okay, so that was some well-known result. So if you have seen this, you may ask, I think it's natural to, okay, retrospectively it's natural. To say it's natural, you may ask yourself, okay, I have this induced current. This induced current, induced current happen in the material system because you can only have this if you have a chemical potential. Now, also only if you have anomaly. In this case, chiral anomaly. Now, if you have the Casimir effect result in your mind, you may ask yourself, can I have something like this in vacuum, in the presence of some anomaly? So that was our motivation. So we found that actually it's possible. You can have some kind of induced current phenomena in vacuum. If you have Weyl anomaly and also a boundary. So this is what I want to explain. So actually to arrive at this is not arrive at this result which I'm going to tell. It's not because we are thinking about induced phenomena. It's just because it's very actually completely natural that after you have done this analysis for Casimir effect, right? It's for a second rank tensor concern. So if you want to generalize, what would be better to consider a consider current, which is conserved and first order, first rank. So it's completely parallel analysis. So for current, you can have an asymptotic expansion around the boundary and conservation that allow you already in a flat background, of course, otherwise it would be too complicated. In a flat background, but with the EM flux, and you can determine this coefficient 0. The leading one will be 1 over x, and the coefficient will be something like this. So it will depend on the EM background or the curvature of your boundary, and then you have some coefficient here. I call it alpha. You can call this current coefficient in this case. So similarly, one can establish a relation between variation of the Weyl anomaly, boundary Weyl anomaly, and this like a work term here. The Weyl anomaly in general, when people talk about Weyl anomaly, maybe 95% of the time people will be referring to the metric contribution to the Weyl anomaly. But actually, in particle physics, so depending on which community you talk to, there's a lot of application of Weyl anomaly, which is coming from the gauge field back contribution for the Weyl anomaly. So the Weyl anomaly from the gauge field contribution actually is just an F squared term. The coefficient V1 here is coming from the beta function. So I mentioned in the beginning, the combination of Weyl anomaly, you actually have to complete some diagram and get some beta function. This is what I mean. This is actually first computed again in the 70s by John Ellis and Collins, all these quantum field theory fathers, so particle physics leaders. And so what I want to do is apply thinking about this and try to learn something using this relation and using this long result about Weyl anomaly in the presence of EM background to derive the form of the current near the boundary. So it's again very simple. We substitute into here, and then using this interpretability condition, we can determine the relation between the current coefficient and the and this B1, this anomaly coefficient, this boundary central charge. So we get this after you put back the dimension. You have this. So this E squared COH bar is actually well-known unit called a quantum Hall conductance. And then you have this. B1 is the beta function. So this is something you can follow, but then of course you feel unsatisfied because what's the physics of it? How can you have something pop out in a vacuum, just turn on a B field? I mean, it will be surprising if you don't feel surprised about this phenomena. Okay. So there are two ways you can I can try to give some physics of this phenomena. The first is that actually this is related to vacuum fluctuation of the vacuum, like Casimir effect. You always have pair creation of the vacuum. In the presence of a B field, this pair created particle, electron, they will try to combine, but before they combine, they have to move on the circle because of the B field. So they move on circle, so combine here, for example. That would be the case if this point of creation is very far away from the boundary, then they will have enough time to combine. Or if there's no boundary at all. But in the present boundary, some of these created particle, which if they're close enough to the boundary, and if the velocity which they created slow enough, then the circle will not have enough time to complete. They will get refracted from the boundary. So that effectively gives you a separation of charges, and that's the origin of current. That's one way to see it. The other way is equivalent, but I actually like the second way even more. It's due to magnetization of the vacuum. It's a magnetic magnetization. So again, it's a creation of charges. You have two charges created. They move on circle. So now I just draw a different picture of the charges. So here is charges created from this point and then going around. So this is actually charges created by two different processes. But then I consider those charges which are overlapping on the same circle. Yeah. So if you look at the individual charges, they actually correspond to a highly current loop. So that gives you a magnetic dipole. The opposite charge particle will go in the opposite direction because of Lorentz force, but the charge is also opposite. So they create the same magnetic dipole. So actually, this if you turn on a B field, then effectively there's a infinite density of magnetization in the vacuum. But usually, of course, this is not observable because it's just a uniform magnetization. It's you subtract it out, so it's not observable. But in the presence of boundary, again, some of these we cut. For example, if this is too close to the boundary, it will be cut. So you actually create a non-uniform distribution of magnetization density, infinite, but the closer to the boundary is less infinite. So if you subtract out the infinite top, then you get 0 at infinity, far away, and then something residual left over near the boundary. So you get some finite distribution of magnetization density. And that gives you a magnetization current. This is the origin of this current. Yeah. So there are various things you can try to think about this current. So if try to measure it or try to find application of this presence of this magnetization, it should have some observable effect. We are thinking about that. Okay, so now let's go to comment chapter 15. Okay. Yeah. So let's go to the second part. When this can be understood, this current can be understood also in terms of BCFT. Both the Casimir effect and this current can be understood in terms of BCFT. So let me just give some very quick background about what BCFT is about. So this is actually originated from Anomaly in 2011. So he just thought, okay, if I have a theory, this M is a manifold where my conformal field phi is defined. So obviously you have a boundary which is given by this P here. So what's the dual of this? So the natural thinking, naive thinking would be, oh, this is due to a part of the ADS space. So it's given by this. If M becomes the whole space, then this also extends to the whole ADS space. So this is his conjecture. So of course, to make use of this idea, one has to know what is actually the volume, which is due to M. Or in other words, what's the boundary Q, which defines the volume. If you can define the shape of this, then you know the dual. We can define the dual precisely using the standard NCTS-Kyoto machinery. So once you know Q, and we just write down the standard Einstein, Einstein action, and then this is because N has a boundary, so you have a Stephen Hawking boundary term, and because N has not just M as a boundary, also Q as a boundary, so you get also Stephen Hawking boundary term on Q, yeah. And then because M and Q, if you look at this picture, sorry, this picture here, this Q and this M actually doesn't join smoothly in general as a junction, so-called junction in the in gravity literature. This junction, this discontinuity in the normal, we have to fix it also. So to have a well-defined construction of the action, one need is a junction term, so-called. And then he also Tanaka also put in this T, which is like a mass term. It's a free parameter which is allowed, doesn't spoil anything. So the question is how do you determine the shape of Q? So he said, oh, if this is an action, and Q should be chosen so that to minimize this action, such a minimization. So it's reasonable, very reasonable. So if you do that, you get this equation. So it's an equation about the exterior curvature. So it's very much like the Einstein equation, except it's the Einstein equation for the boundary metric. Yeah. But there's a problem here. The problem is that Q is a dimension 1 surface. So in general, you just need one function to determine the shape of Q. For example, if you take the vertical direction, the horizontal direction as C, then to determine Q, you just need to know what C is as a function of xi. Xi is a coordinate of M. So it's like you want to know this surface is like a camp over your ground. You just need to know the height of this camp at each one of the ground. Just one function here. But in general, this embedding equation contains too many equations. It's a tensor set of equations, an Einstein equation. So there's no solution in general, except a very simple case. So when we look at this problem, we thought equation of motion is fine, but then actually there are many ways to get this equation of motion. So here is assume that one impose one boundary condition on Q, but you can also impose other boundary condition, and the next one is to impose a mixed boundary condition, so that you get the trace, the scalar part of the tensor equation. And then you look at this, and then everything is fine, it's consistent. And you can do this for any for general shape of the boundary. Right? So let me skip that part. So even after you have the proposal, so you have assuming we can now use this to work out the shape of Q, and then put it back to the action, and then compute everything. There's still one technical point that one has to pay attention to. In the standard NCTS-Kyoto, usually one has to assume the Einstein, the Buck metric as a expansion called FG expansion, Ferriman-Graham expansion. So it's a assumption about this the Buck metric that this can be proved. One can show that any ADS, not the ADS metric, take this form where this G has a perturbative expansion like this. So this is a mathematical theorem by them. And the coefficient can be solved and given by this by putting this back in the Einstein equation. But now there's a problem because, as I said, because of this singularity here between M and Q. So there's some technical assumption which we haven't worked it out. We think there must be some technical assumption given in this proof of mathematical proof that this should break down. Now, if you give up the FT expansion, then just try to solve Einstein equation. Try to solve Einstein equation exactly, and it's hopeless because it's just too complicated. So instead, we find a different way to do expansion. So the reason why we want this FT expansion here is just because with FT expansion, you have the perturbative expansion to the answer of the metric. So when you solve Einstein equation, you get some simplification so that you can solve it. So here we find that actually we can have a different type of expansion, perturbative expansion, so that we can still solve Einstein equation. The expansion we introduce is we have a metric, we have a boundary here, and the boundary metric in general we can say in this form. So x is okay. P, the boundary is located at P, x equals 0. So it's like this is your M, this is your boundary, this direction is x. So when x equals 0, you're at the boundary. At the boundary, then you have a boundary metric, which is sigma AB, dy A, dy B. When you go inside, then the metric can become more complicated, depending on x, of course. So in general, there will be expansion. So like x to the power 0, x to the power 1, x squared, etc. Some coefficient k and q. So these k and q, this is actually a derivative expansion. I mean, you can look at dimension. So k is the first derivative of sigma, q is second derivative of sigma. So this is exact derivative expansion. So we assume you can have a expansion, perturbative expansion. If you assume k and q, or in other words, the derivative is small. So by using this derivative expansion, then we can still solve Einstein equation. So this is the result. It's quite interesting because it shows a non-analytic behavior of x here. X is the distance from the boundary, so it's 1 over x here.
So,
Yeah.
sorry, just to fill the gap of my ignorance.
Yeah.
So, is a Graham-Fetterman expansion a unique one that's asymptotically ADS?
Yes. But they have.
Is that the only assumption here?
So I read their paper. So at least I cannot go through the paper, but in the beginning they will say, oh, assume you have some asymptotic ADS metric, and then blah blah blah, and also
I can see
homologically a sphere, then you can arrive at the expansion. But they usually when mathematicians say they have some homologically like a sphere, that kind of thing, I think they have some smoothness condition assuming implicitly. So here I can construct something which is different from that. It's not FT expanded. So this is something which certainly also still asymptotically ADS, because asymptotic ADS is about this C direction, right? So
yes,
that must be. So I think there must be something hidden in there.
Yeah. So the boundary is z equal to 0.
Yeah.
Right. And
so this function is equal to 1.
Fine.
I think.
Is that the only assumption they are making, that the spherical?
Yeah, topological. This is topological.
Oh, yeah, exactly. It should be topological.
Yeah. This is also topological sphere, except this is geometrically you can see some discontinuity of the normal.
And do you think this will break down?
Yeah.
I see. Because of what?
No, I mean, if you look at this, there's no way you can capture this discontinuity.
Okay, so it means some additional source which will break the.
Yeah, I mean, the discontinuity of the normal is you differentiate, for example, the metric in this normal direction. Then even if you shift a little bit, and you will get different, the way you approach this point here, depending on how you approach it, then it will be very different. The derivative will be very different. So, yeah, okay. So we use this and then together with the embedding equations, and then we can fix the shape of Q. So now we can do the ADS BCFT. So for example, now we turn on the standard case, we turn on because we are interested in current. If the current is coupled to A, and so it's due to a background Coulomb field in the bulk. So we turn on this, and then we do the standard computation, just for the time. So just told you. So we get this 1 over x, and then this X A. So decided this gives the form of the current you have in the field theory. So now let me go to the final part, 6 dimension. In 6 dimension, we can also talk about current, but the current is not caused by current of a point particle. It's caused by current of a movement of a string. So in a point particle, you have a current density like this, and then the minimal coupling. This is the minimal coupling. You just integrate this over the space, and then you get the standard minimal coupling over the Weyl line of the particle. So the same. This is really an inventory just for the student here. Yeah. So a string will move like this. So you have a string Weyl sheet, and you create current density for the string, and then you created the minimal coupling for the string to the B field. So the question is, what's the implication of having such a coupling? So we saw already this coupling, this minimal coupling, is related to anomaly, and so this should be related to anomaly also. So in fact, we find such a relation. So the boundary Weyl anomaly. So this can be proven in general using just a field theory, assuming you have the partition function, and then you can show this. You don't need Lagrangian. So one can prove this. This equation here is just to say that the general structure of Weyl anomaly has been studied. The metric part is the answer is known by this gentleman here. So you have the standard Euler character contribution, and then you have a number of couple invariant which you can construct, and they all contribute to the Weyl anomaly, and with coefficient A coefficient and C coefficient. But the contribution, a similar equation for background flux has never been written down before. So like the one with F squared, that one has never been written down before. So now let me go to ADS BCFT. Just put in the like a Coulomb term now in 7 dimension. Then one can derive the current with coefficient. This B1 is related to the coefficient, the overall normalization of Newton constant. So basically the Newton constant. So in field theory, if one put it back to this relation, then one can derive the anomaly. So this is the answer. So this, of course, you see this and you say, oh, it's actually trivial because it's just F squared generalized. Okay, but it's still, I think the answer is trivial, but the way you get it is not trivial, and maybe it's not completely trivial if you have not seen it before. Okay, so how do you get this in field theory? This is not known, but in 4 dimensions, for example, to get the F squared, this is what you have to do. You couple, you consider external background gauge field. So this background gauge field is modified by loop. So this loop can spoil the contribute term to the interaction, which spoil couplable symmetry. This is how we do it. So for example, you have an electron here. So in 6 dimensions, you would try to put B field here, B mu, and then couple to some 2,0 field here. But the problem is in 4 dimensions, the A is coupled to matter field by minimal couple. So the Yang-Mills 7 Yang-Mills construction. And in 6 dimensions, we don't know the minimal coupling for B field. Right? So this is something unknown. So it's an open question how to derive the anomaly from field theory. Now if one apply this so everything I said here, everything I said here is something to do with M5 ring. And now let me apply the M5 ring, which is a particular case in which we know W is ADS7S4, and then we also know the coefficient in front, Newton constant, and the radius. All these are determined by the ADS7S4 geometry. So in terms of n, so in the end you get n cubed. You have to do some really simple algebra. So we find this current here. So the current itself, for also n cubed, suggests that there are n cubed degree of freedom running around some loop. Although we don't know how they couple, but if this picture is there, then there will be n cubed number of particle moving in the loop. So it suggests at least there will be n-cube degree of freedom coupling the B field. So probably the whole two-gamma zero theory has n-cube degree of freedom. There's a missing link here. Of course, it's possible that there's some degree of freedom in the two-gamma zero field is neutral to the B field, but it's probably not the case because this usually maximal supersymmetric field. Everything is next to each other under case symmetry. So in any case, it suggests that there are n-cube degree of freedom in the two-gamma zero field. Let me conclude. We found some new universal relation for linear boundary behavior for the stress tensor, which is called the Casimir effect, and the current. In the presence of B field, we predicted a magnetization current in the vicinity of the boundary of a QED vacuum. Somebody suggested to me, oh, you can call it a magnetic Casimir effect. Well, I think it's a nice way to put it. So, for boundary homomorphic theory, we have constructed a new class of metric, which is non-FG expansion. So this metric will be essential whenever one wants to do some BCFT analysis. Also, we have predicted a Weyl anomaly for the M5 ring system. So this can be also generalized to, of course, to any even dimensional field. But the crucial problem is how to understand this Weyl anomaly of the field theory and maybe construction of the covariant loop. Yeah, thank you.
Sure, questions, comments?
As for the second item on this slide, so I think that this may be a kind of magnetic Schwinger effect.
Oh, Schwinger effect.
So like in the Schwinger effect with external electric field, so I think that you need to impose a very strong magnetic field to get this in this time in your experiment.
No, there's no constraint on the magnitude of the current. First. Second is the Schwinger effect is still different because it's on shell. In the end, you actually create a charged particle. This is, I think, it's completely magnetization effect. There's actually no real particle in the end which is created. It's a magnetization, background magnetization, like magnetization current. Yeah. So there's no lower bound on the B field to observe this.
As long as you can get very close to the surface.
Yeah, I mean the
Casimir.
Yeah, not close, so that this results, of course, if you are so close to the atomic level, then you start to see that is structure and then the quantum field theory break down. So up to certain, and I think you can see